So let's take a look at the cross product. Now the cross product is going to be that second method for multiplying two vectors. And so in the dot product we wrote a times b like this, but in the cross product we'll write it like this. So for number one, let's find the cross product of a and b. And a has the components 1, 2, 0, and b has the components 0, 3, 1. So in order to find the cross product, we must set up a matrix. And so we have to set up a 3 by 3 matrix here, with I, J, and K being on the top row. So we have I, J, and K. And so I, J, and K are obviously the unit vectors. And so I represents the x components, J is going to be the y components, and K is the z components. Since A is first, we're going to put A's components from left to right, so 1, 2, 0. And then on the third row we put B's components from left to right, so 0, 3, and 1. So now what we have to do is take the matrix and write it in determinant notation. And what that basically means is that, let's say we have to pick the top leftmost value here, I. So we write I, and then we're going to cross out the row and column I is in, so we cross those out, and then we write what's left inside in another matrix. So we have 2, 0, and 3, 1. So 2, 0, and we write them in order, exactly the way they are in the matrix. And then we put a minus sign here because the next term is going to be a negative. And then we have the next one, J. And so we're going to cross out the row and the column J is in. And then we write what's left. So we have 1, 0, and then 0, 1. So we're going to write that inside the matrix. So 1, 0, 0, 1. And the next term is going to be positive, and then we have our third value, K. We're going to cross out the row and the column it's in, and then we're going to write what's left here. So 1, 2, 0, 3. And then finally what's left to do is to cross multiply and to evaluate. So we're going to start from the leftmost, or the top leftmost value, so 2. We cross multiply it with 1, and we cross multiply 0 with 3. So the very first thing we're going to do, I'm going to put I down here. So we multiply by 2 times 1, which is 2, and then you always subtract the next cross product. So 3 times 0 is obviously 0. So the next one's a minus. So we put minus J. Now we're going to cross multiply 1 and 1, and then we're going to subtract the cross multiplication of 0 and 0, which is 0. And then plus K times cross multiply 1 and 3, we get 3, and then minus cross multiply 0 and 2, which we get 0. So to evaluate, we get 2 minus 0, which is 2, so 2 times I, minus 1 times J, so just J, and then plus 3K. So that is going to be equal to the cross product of A times B. So realize that unlike the dot product where the result gives you a scalar value or some multiple or constant, the cross product will actually give you another vector. So that is the final answer. So for number 2, A equals 2I plus J minus K, and B equals J plus 2K. So in order to find the cross product here, A times B, we're going to go ahead and set up the matrix once again. So we have I, J, and K. And so I goes with the x components. So since A is being multiplied first, we go ahead and put its components from left to right. So we got 2 with the I component, 1 with the J component, and a negative 1 with the K component. And for B, we have nothing for the I component, so that's going to be 0. For the J component, we have 1, and for the K, we have 2. So that is going to be our Z component there. So now let's go ahead and write it in determinant notation. So we go ahead and pick the first value, which is I. We take I, we cross out the row and the column that it's in, and we write what's left inside another matrix. So we have 1, negative 1, and 1 and 2. We're going to subtract the next one, so J, cross out its row and column, and write what's left. So we have 2, negative 1, and then 0, 2. And then we add the third value here, so plus K times the matrix. If we cross out the row and column K's in, we have 2, 1, 0, 1 that's left. So now when I evaluate, we'll go ahead and cross multiply. So we have I times 1 times 2, which is 2, minus negative 1 times 1, which is -1. Minus the -1 means +1. Then we have minus j times 2 times 2 is 4, and then minus 0 times -1, which is 0. And then plus k times 2 times 1 is 2, minus 0 times 1, which is 0. So 2 plus 1 is 3. That'll give us 3i minus 4j, and then plus 2k as the cross product of a times b. Now before I move on to the next question, the cross product of a times b yields another vector, and this vector is perpendicular to both vectors a and b. So let's go ahead and find a unit vector that is orthogonal to both 1, -1, 1 and 0, 4, 4. So once again, another word for orthogonal is perpendicular, and like I just mentioned earlier, a times b, the cross product, yields another vector that is perpendicular or orthogonal to both vectors a and b. So let's go ahead and call 1, -1, 1 vector a and 0, 4, 4 vector b. Let's go ahead and take the cross product of a times b. So once again, we're going to write a matrix, or we're going to create a matrix here with values under values I, j, and k. And since a is being multiplied first, let's go ahead and write its components from left to right. So 1, -1, and the z component of 1. And then b's x component is 0, y component 4, and z component 4. And then let's go ahead and put it in determinant notation. So we're going to start with I. So we have I times a matrix. Now let's go ahead and cross the row and column that I is in. So what we have left is -1, 1 and 4, 4. So next we have minus the next term, which is j. So we go ahead and cross out the row and column of j, and we have 1, 1 and 0, 4. And then adding the third term k, when we cross its row and column out, we get 1, -1 and 0, 4. So let's go ahead and cross multiply. So we get I times -1 times 4 gives us -4, and then minus 1 times 4, which gives us 4, minus j times 1 times 4 is 4, minus 0 times 1, which is 0, and then plus k times 1 times 4, which is 4, minus 0 times -1. So we end up getting -8i minus 4j, and then plus 4k as the result of the cross product of a times b. So this vector is going to be orthogonal or perpendicular to both vectors a and b. But notice it's asking for a unit vector. So remember a unit vector. Let's say we just have vector a. The unit vector for vector a will be the vector in its component form over the magnitude. So basically, in order to do this, we have to find the unit vector by taking what we found for the cross product and dividing it by its magnitude. So if we were to write the resultant vector in its component form, we can just write it as -8 because that goes with the x component. J goes with the y component, so we have -4, and then 4 is our z component, so that goes with k. And so that is going to be our a times b, or the cross product, and its component form, and we're going to divide that by its magnitude. And so remember, if we take the magnitude of a vector in its component form, we have to take the square root of the x component squared, so -8 squared is 64, plus its y component squared, 16, plus its z component squared, 16. So we get 64 plus 32, or the square root of 96. Now 16 times 6 is 96, so we can also simplify it to 4 times the square root is 6 as its magnitude. So we can go ahead and divide it. Since the 4 times the square root of 6 is going to be the magnitude of the cross product, we go ahead and divide it by 4 times the square root of 6. And since 4 times the square root of 6 sort of acts like a multiple, we can go ahead and divide each component in the vector by the magnitude. So we can rewrite it as -8 over 4 times the square root of 6, comma -4 over 4 times the square root of 6, comma 4 over 4 times the square root of 6. So when we simplify, we'll get negative 2 over square root of 6 as our x component, negative 1 over square root of 6 as our y component, and just standard 1 over square root of 6 as our z component. And this is a unit vector that is orthogonal to both vectors 1, negative 1, 1, and 0, 4, 4. So now let's say we have two vectors a and b. So I'll call this vector a and this one vector b. And using this we can go ahead and create a parallelogram. Now in order to find the area of this parallelogram, all we have to do is take the magnitude of the cross product of a times b. So for number 1, let's go ahead and find the area of the parallelogram with vertices a, 2, negative 1. So if I were to draw this in a two-dimensional plane here, so a is, negative 2, 1. So that's going to be a. We have b at 0, 4. So around here. C is at 4, 2. And then we have d at 2, negative 1. So this is going to be approximately the parallelogram. So remember, the area of the parallelogram is going to be the magnitude of the cross product of two vectors. Let's just call them a and b. So let's go ahead and make two vectors then. So I'm going to go ahead and cancel out the line segment BC and line segment DC here. And then I'll make two vectors here. This one is going to be vector AB, and the other one is going to be vector AD, since we only need to represent two vectors. And remember, we can represent line segments as vectors by using the simple formula where we take x2 minus x1, comma, y2 minus y1. So let's go ahead and start with AB, vector AB. So I'll go ahead and write AB here. So if A is our first set of points and B is our second set of points, we go ahead and take x2, which is 0, minus x1. So 0 minus negative 2 would give us 2, comma, y2 minus y1. So 4 minus 1 gives us 3. So that is going to be the vector that represents the line segment AB. Now for vector AD, once again we're going to use the same formula. So we're going to take x2 minus x1. So 2 minus a negative 2 gives us 4. And then comma, y2 minus y1. So negative 1 minus 1 gives us negative 2. So that will be the vector representing the line segment AD. So now I'm going to go ahead and rename vector AB as just vector A, and vector AD as vector B, just for simplicity. Vector A and vector B here. And so now what I can do with these two vectors is use the area formula. So let's go ahead and find the cross product of vector A and B. So once again we're going to create a matrix here. So once again we need the top I, j, and k variables on the top first row. And so we go ahead and lay out the components. So first being multiplied is A, so we go ahead and put 2 as the x component, 3 as the y component. And notice there is no z component, so it's basically 0 under the k. And so the same thing with B. We have 4 as the x, negative 2 as the y component, and 0 as the z component. So now we can go ahead and put it in determinant notation. So we first start with I here. Take I, cross out the row and column i's in, and so we're left with 3, 0 and negative 2, 0 as what's inside the smaller matrix. We subtract the second term j, so we cross that out, we get 2, 0 and 4, 0. And then we add the third term k. And so when we cross out the row and column k's in, we're left with 2, 3 and 4, negative 2 inside the smaller matrix. So now we go ahead and cross multiply. So we get I times 3 times 0 minus negative 2 times 0. So we get 0 minus 0 minus j times 2 times 0 is 0 minus 4 minus 0 is 0. And then plus k times 2 times negative 2 is negative 4 minus 4 times 3, 12. So obviously the zeros will cancel, I and j, and so we're left with negative 16k as the cross product of a times v. So in order to find the area, we must find the magnitude of the cross product. So we've already found the cross product, but now let's find the magnitude. So let's go ahead and write negative 16k in its component form. So a times b will then equal, in component form, the x component is 0 because there's no I, the j component or the y component is 0 because there's no j, and then the z component is negative 16 because that's the coefficient of k. And so now in order to take the magnitude, we must take the square root of the x component squared, which is 0, plus the y component squared is 0, plus the z component squared. 16 squared is 256. And so we take the square root of 256, which gets us back to 16. So that is going to be the area of this specific parallelogram. So now let's say we have the base of a parallelogram, and that is represented by two vectors, b and c. So obviously we know when we have two vectors, we can find the area of this parallelogram being the magnitude of two vectors, or the cross product of two vectors b and c. And so now let's turn this parallelogram into 3 dimensions. So what we create here is known as a parallelepiped. That is just a parallelogram in 3 dimensions. And so now we're calculating volume. And so volume is obviously going to be equal to the area, or that base, times the height. So let's just call the height A, vector A. So we can represent the height also as another vector. So now the new formula here, volume is going to be equal to the magnitude of the height, which is A. So it's going to be the dot product of A times the cross product of vectors B times C. So that is going to be the equation for the volume. And so to put it in simple terms, B times C, the cross product, will give us the base, and then A will give it the height when we multiply. So this is known as the scalar triple product. So let's go ahead and find the volume of the parallelepiped created by the 3 vectors A, B, and C. So once again, the volume is going to equal the triple scalar product, or in other words, the magnitude of A times the dot product of A times the cross product of B times C. So basically A times B times C. Now, the way we set this up is we create another matrix here. So the volume is going to be equal to this matrix, and instead of having I, J, and K as our top row, vector A's components will be replacing the I, J, and K. So they will be the top row. So 6, 3, and negative 1. Now B will be in the second row, so 0, 1, 2, and then vector C will be in the third row, so 4, negative 2, 5. And so in order to calculate this, or in order to solve this, we're going to use the exact same method. So instead of having I, we're going to have 6 as our top leftmost. So it's going to be 6 times the matrix. Now if we cross out the row and column 6 is in, we're left with 1, 2, and negative 2, 5. Minus the next term, which is 3. So we have 3 times the matrix. Now if we cross out the row and column of 3, we have 0, 2, and 4, and 5. And then plus the last term, which is negative 1, times, if we cross out negative 1's row and column, we have 0, 1, and 4, negative 2. So now when we evaluate, we still cross multiply, so we have 6 times 1 times 5, which is 5, minus negative 2 times 2, negative 4. Minus a negative 2 means, or minus a negative 4 means plus 4. And then we have minus 3 times 0 times 5 is 0, minus 4 times 2, which is 8. And then minus 1 times 0 times negative 2 is 0, minus 4 times 1, which is 4. So 5 plus 4 is 9. 9 times 6 gives us 54. So we're at 54 here, minus 3 times negative 8, which is negative 24. So that'll be minus a negative 24, so plus 24. And then we have 0 minus 4, negative 4, minus times a negative 1, so positive 4 here. So 54 plus 24 gives us 78, and 78 plus 4 gives us 82. And so that is the final answer for the total volume of the given parallelepiped. So going back to the triple scalar product, obviously the volume is equal to the magnitude of that triple scalar product. Now if we get 0, as a result of the triple scalar product, that means all the vectors are in the same plane, so they are coplanar. So the main application of the cross product is torque. So similar to calculating work with a dot product, there are two formulas for torque. Now torque can either equal the magnitude of the cross product of the radius vector times the force vector, or it can also equal the magnitude of the radius times the magnitude of the force times sine of theta, or that angle. So let's say a bicycle pedal is pushed by a foot with a 60 Newton force. The shaft of the pedal is 18 centimeters long. Find the magnitude of the torque about P. So since we're given degrees and magnitudes of both the force and the radius, we can use the equation that the magnitude of the torque is going to be equal to the magnitude of the force times the magnitude of the radius times sine of the angle theta. Now because it's in degrees, let's make sure our graphing calculator is in degrees, or if you're in radians, you can also multiply your answer by 180 over pi. So in this case, the magnitude of the torque is going to equal the magnitude of the force, which is 60 newtons. We have 60 times the radius. Now keep in mind that torque is also calculated in Newton meters or joules, and so we have to convert centimeters to meters in order to do the correct calculation. So 18 centimeters is 0.18 meters, and then multiply by sine of the angle. Now keep in mind, this angle is 10 degrees, and then we're going an extra 70 degrees. So we're going a total of 80 degrees. And so that should give you a final answer for the torque being around 10.6 Newton meters or 10.6 joules.